This video talks about quantum computation. Before you guys roll your eyes at me, let's play again. A coin game. At the very beginning, we initialize a coin as tails. I play with a coin first. I could flip it or do nothing. I write down my choice on a piece of paper but keep that from you. Then, you play with the coin. Similarly, you make your own choice without revealing that to me. Lastly, I decide if I want to flip it or not. After these 3 rounds, we look at the coin. If it's tail, I win, but if it's heads, you win. So, what's the probability that you win the game? We could list all the outcomes and calculate. As you can see, both of us have a 50% chance to win. However, what if I was not a human? I was a quantum computer instead. What would be the odds that you win? Someone actually did such an experiment, and you could repeat the same experiment yourself on IBM Quantum Experience. It's a free platform where you can play with a real quantum computer. You just need to sign up, get an account, and try that out. I'll put the link below. Anyway, here are the results from over 8,000 repeated games, which shows that if you played against a quantum device, it was likely that the quantum computer would always win, and it lost only due to operational errors. Why is that? Did the quantum computer cheat? Of course not. Actually, this comes from the nature of quantum physics. We use 1 to denote the heads and 0 for the tails. For a classical coin, it could be either heads or tail at one time. In contrast, a quantum coin could be in a superposition, a combination of heads and tail, with some probability of being heads and some probability of being tails. How should we describe the state of a quantum coin? How should we express the superposition of both heads and tails, both 1 and 0? Well, we use a vector similar to this one. And if the coin is only in heads or tail, not a superposition, we write them as this. However, you might already see the problem with this vector describing the superposition. It looks like a combination of 100% heads and 100% tails, but the sum of our probability should be 1. So we introduce probability amplitude. If you know quantum physics, this should be obvious to you. If not, I'll make another short video for that. No worry anyway. What we need in this video is that the probability amplitude are complex number whose squares are probabilities. So, a quantum coin can be described by this vector. This one is a probability amplitude. We call this vector state vector. A quantum coin is fundamentally different from a classical one, but it could disguise itself as a classical coin. That is, being in heads or tail for 100% of the time. We call such states classical states. These two are classical states because they look classical. We note that even though the chances of heads and tail are half-half here, it's not a must for a quantum coin. It could be 18 to 20 or any kinds. Then, how could we change a tail or head into a superposition of heads and tails? The answer is Hardman Gate. What does a Hardman Gate do? Well, the Hardman Gate can be described by this matrix. For a classical state, it transfers the state into a superposition, a pole state. So in the first round, when I play with a quantum coin, I could apply a Hardman Gate so that I get a quantum coin in this kind of state, a superposition of heads and tail. If a Hardman Gate is applied to a head, we got this. Of course, probability can't be negative. These numbers are amplitudes, not probabilities. The probabilities as the square of the amplitudes. In the second round, because the quantum coin is in such a combination of 50% cat and 15% tail, it remains in this superposition whether you flip it or not. Flipping a coin is described by a Pauli X gate. Mathematically, we could write Pauli X gate as this matrix. Then it should be clear why the state of quantum coin stay intact in the second round. In the third round, I apply another Hardman gate to this quantum coin. If we do the math or write down all the possible cases, I would get a tail with a 100% chance. Let's briefly review the whole game. See, it would always end with tails. The Hardman gate, the superposition, is the key. A quantum coin may be counterintuitive to you, but in fact, the fundamental particles like electrons and photons do behave this way. What we've learned so far? We've learned state vectors and gates. In quantum computing, specifically the quantum circuit model, we use quantum logic gates to represent operations we do on our quantum coins. They can be described mathematically by matrices. When we apply operations, we do matrix multiplication. If you are familiar with that, you may know that it is a transformation of the vector. For example, matrix multiplication can rotate the vector, which is what the two gates do for all state vectors. Corresponding to vector space, for quantum coin, for state vectors, we use block sphere. The state vectors point to specific points on a block sphere, which are certain quantum states. The two quantum gates rotate the quantum state in the block sphere. In this coin game, we did 2 to 3 operations during the 3 rounds. Mathematically, the procedure is like this. For the quantum coin, we usually call them qubit, corresponding to bit in classical computing. However, you may have another question now. If the quantum computer could always win, why does it lose sometimes? Actually, here is another round from a real quantum computer with over 8,000 repeated games. Why we didn't get what we expect? Math never lies, and we calculate the procedure. Well, that is because of the errors. Current quantum computers are prone to errors. Errors in quantum computation are usually classified into 3 kinds: state preparation errors, gate errors, and measurement errors, also named readout errors. If we want to propel an excited state 1, but got a ground state 0 in reality, that is a state preparation error. Similarly, if we measure a ground state 0 but got an 1 as a result, that's a readout error. Note that in some cases, we also consider the errors happen in gates used to propel a certain state as state preparation errors. Likewise, errors in gates used to propel a certain measurement basis as measurement errors. Strictly speaking, this is not right, and it's not everyone does in this manner. Some do, some don't. Quantum error correction has mostly focused on gate errors, partially because the state preparation and measurement errors only occur at the beginning and the end of the circuit or an error correction cycle. And unlike gate errors, they do not accumulate with circuit depths. A consequence of this difference is that surface code error correction, maybe the most promising error correction technique, is much less sensitive to measurement errors than to gate errors. Gate errors should be more important in the future when we have more full-fledged quantum devices and work on long and complicated quantum simulations. However, In near-term quantum devices, which are not error-corrected, we mainly focus on simple, practical quantum simulations, approximate optimization, hybrid quantum classical algorithms. That is, we mainly focus on short-depth quantum circuits. State preparation and measurement errors are important for their accuracy. Especially they may increase with register size due to increased crosstalk. We usually call state preparation errors plus measurement errors as span errors. They limit the performance of current noisy intermediate-scale quantum computer and the potential for practical applications. There has been lots of exciting research on errors. I also have several advanced videos about that topic. The fact that this world is essentially uncertain is certainly intriguing. So, muggles, welcome to a magical quantum world.